Hey, welcome to today's lecture on MOSFET, the matter, matter oxide semiconductor uh, field effect transistor. Okay, so these remarkable devices used in modern integrated circuits or IC are the workhorses of modern electronics, which are serving as the fundamental building blocks of nearly every electronic device you are using on a daily basis. So let's imagine that MOSFETs as the tiny gatekeepers of our digital world, billions of microscopic switches that control the flow of information in your smartphones, laptops, and even your refrigerator. So in order to understand its importance, think of a modern city's traffic system. Just as a traffic lights control the flow of vehicles through intersections, MOSFETs control the flow of electrons through circuits. However, unlike a traffic light that simply stops or allows traffic, MOSFETs can regulate precisely how much current flows, similar to how a water faucet can be adjusted from a trickle to full flow. So this ability to amplify and switch signals with precision and efficiency has revolutionized our world. So today in this lecture, we are going to explore how these devices work, their structure, and the principles that govern their operation. So while the physics may seem complicated at first, I'm going to use familiar analogies to make these concepts accessible. So whether you're from an electrical engineering background or joining us from another discipline, by the end of this lecture, you are going to appreciate how these tiny transistors have become the foundation of our information age. Okay, so here is the outline, structure and operation of the MOSFET. So in this lecture, we will focus specifically on the structure and operation of MOSFETs. So think of this as learning the anatomy and physiology of these electronic devices, just as understanding how the heart pumps blood helps us comprehend the circulatory system. Understanding how electrons move through a MOSFET will reveal how complex circuits function. So we will begin by exploring the basic structure, the layers and materials that make up these devices, MOSFETs. And then we will examine how they operate, the underlying physics and behavior when voltage is applied. The beauty of MOSFETs lies in their elegant simplicity and versatility as well. So despite being incredibly small, modern transistors measure just nanometers in size. They follow consistent principles that we can model and predict. So as we progress through this all material, I encourage you to think about everyday analogies. For example, the gate of a MOSFET controls current flow, much like a garden hose nozzle controls water flow. A small amount of pressure on the trigger, or which is equivalent or corresponding to the voltage at the gate, can control a much larger flow of water or current through the hose. So these mental models will help you grasp and understand the concepts regardless of your background. All right. So now let's move on to the next slide. So the journey of the MOSFET begins back in 1935 when Oscar Hale was issued a British patent um, for a field effect device. However, the idea remained largely theoretical until 1955 when a working MOSFET was finally demonstrated. So think of this 20-year gap as similar to the time between Leonardo da Vinci sketching flying machines and the Wright brothers actually achieving flight. So the concept existed long before the technology could make it reality. So looking at Hale's original pattern drawing, as shown in here, we can see the fundamental elements that would evolve into today's transistors. So the design may seem primitive compared against the modern devices, but it contained the essential insight. Using an electric field, right, to control the current flow from place one to place two through a semiconductor, which is corresponding to the number three. So this was revolutionary, thinking at a time when vacuum tubes dominated electronics. So this gap between conception and implementation reveals an important lesson about technological innovation. Great ideas often await the development of materials, manufacturing techniques, and supporting technologies before they can be realized. So in this case, advances in semiconductor processing and material sciences were necessary before MOSFETs could become practical and real. So today, when you use your smartphone or laptop, you're benefiting from an idea that took decades to mature from concept to implementation. So it always takes time to implement something new. All right. So now let's take into the some fundamental working principle in modern field effect transistor FET. So the modern field effect transistor operates on a principle that might seem magical. However, it can be understood through a simple analogy. So imagine again a garden hose representing our semiconductor, where water representing electrical current in our device flows from one end to the other end. Now, imagine you can squeeze these hose from the outside, controlling the water flow without directly touching the water itself. This is essentially how a FET works. We apply an electric field from outside the semiconductor. Take a look at here. We are going to apply electric field from the top gate electrode uh, from outside of the semiconductor. Here is semiconductor, right? So uh, from uh, from outside the semiconductor, using vertically directed electric field, we can control the current flow inside the semiconductor, right? So more specifically, an electric field is applied, as I told you, perpendicular to the surface of the semiconductor by applying what? Yeah, a gate voltage on an electrode above semiconductor. So separated by an insulating oxide layer. So this silicon dioxide layer. So this electric field, so this electric field modulates the conductance or resistance of the semiconductor beneath. So in practical terms, we control the drift current from drain to source between two contacts here, from drain to source, called the source and drain. Okay. So by varying what? By varying the voltage on the gate electrode. So in order to flow a current from uh, drain to source, you don't need to modulate the voltage difference between drain and source. You should modulate the third terminal, which is called the gate, to control what? To control the current flow from drain to source, right? if you imagine a resistor, in order to control the total amount of current value between throughout this resistor, you should modulate the voltage, right, between two terminals. So the current flow from terminal one to terminal two is fully controlled by the voltage difference between terminal one and terminal two. Okay. So these voltage and currents are directly associated. However, in FET, the current from drain to source, IDS, is not the function of the voltage difference between the drain and source. Okay, so this is the main point. Why the FET works very different from the working principle of the resistor. Okay, so let's think about the source again. So here, think of the source as a reservoir of electrons, and the drain as where these electrons flow to, and the gate as a valve controlling this current flow. So when you turn a water faucet handle, which is corresponding to the gate, you're not directly touching the water, right? However, you are controlling how much water flows from the pipe to the sink, right? In MOSFET from source to drain. So in similar, the gate voltage creates an electric field that either allows or restricts electron flow through the channel. So without the gate current directly entering the semiconductor. Okay. All right. So that is a main uh, working principle. So now let's take a look at the 3D bird's eye view of planar bulk silicon MOSFET. Let's see. Okay. So the bulk silicon MOSFET represents the classic device architecture that has dominated computing for decades. So looking at these, its structure, we can identify the key parts: the gate, source, drain, and substrate or body. So if a MOSFET were a kitchen faucet, the source would be the water pipes bringing water in. The drain would be the sink where water flows out. And the gate would be the handle that controls the flow. So the name metal oxide semiconductor field effect transistor actually describes its layered structure, right? MOS, layered structure. A metal, or more commonly now polysilicon or metal gate, and sitting on top of an oxide insulator, which sits on a semiconductor substrate. The key dimensions that define its performance are the gate length, L sub G, oxide thickness, Tox, and junction depth, X sub J. As these physical dimensions scales down, transistors become faster and more energy efficient, similar to how reducing the size of an engine while maintaining its power makes a car more efficient. The most desirable characteristics for MOSFETs are high on current for speed and low off current for energy efficiency. So think of this like a light switch that can turn on very quickly and brightly when needed, but when off, consumes virtually no power. So MOSFET technology comes in two complementary flavors, N-channel and P-channel, which operate in a complementary manner. When combined as CMOS complementary MOS, they create extremely efficient digital circuits, much like how a well-coordinated dance between partners achieves movements neither could perform alone. Okay. So now let's take a look at the N-channel versus P-channel. So N-channel MOSFET NMOS, P-channel MOSFET PMOS. So those two MOSFETs are like mirror images of each other, working with opposite types of charge carriers. If N-channel transistors are like workers who move packages from left to right when given a signal, P-channel transistors are like workers who move different packages from right to left when given their signal. So for an N-channel MOSFET, current flows when the gate to source voltage from here to here, from gate to source voltage exceeds a threshold voltage V sub T. Okay, here. So think of this like a spring-loaded door that only opens when you push with enough force to overcome the spring tension. In an enhancement mode, um, in an enhancement mode device, this threshold VT value is positive, meaning you need to apply a positive voltage to turn it on, like a light switch that's normally off until you flip it up. In depletion mode, however, the threshold voltage is negative, meaning the transistor is naturally on unless you apply a negative voltage, which is like a light switch that stays on until you dim it down. So p-channel devices, PMOS operate with opposite polarities. So current flows, say this is source and drain. So current flows when we uh, gate, we source to gate. So VGS, say, okay, in order to avoid any misunderstanding. So VGS, when VGS is less than threshold voltage, then the current flows. So in these PMOS devices, the enhancement mode has a negative threshold voltage, while depletion mode uh, has a positive threshold voltage. So imagine a water valve that opens when you pull down instead of push up. It achieves the same purpose but operates in reverse, right? So this complementary behavior gives the circuit designers tremendous flexibility, allowing them to create extremely efficient logic circuits by combining both types, each handling different parts of the operation. All right, now let's take a look at the enhancement mode versus depletion mode. So enhancement mode, depletion mode, two MOSFETs reflect two fundamentally different philosophies of operation. Think of enhancement mode device as a normally off, okay? And depletion mode as normally on. So similar to how light switches can be designed to be either on or off if they are default position. In their default position. So in enhancement mode, conduction between source and drain regions is enhanced by applying a gate voltage. This is like a garden that's naturally dry until you turn on the sprinkler system. The channel doesn't exist until you create it by applying voltage to the gate. Most modern digital electronics use these enhancement mode devices because they consume no power when idle. A crucial feature for battery powered devices, definitely. Depletion mode devices take the opposite approach. A channel already exists when no voltage is applied, and a gate voltage must be applied to deplete or remove the channel region to turn off the transistor. So this is like a garden with a sprinkler system that's always on unless you actively turn it off. These devices can be useful in certain analog circuits or as pull-up registers, but they are less common in modern digital designs because of their power consumption when it is idle. When it is idle. So the diagram here shows the physical difference. In enhancement mode, there is no channel when gate voltage is zero, while in the depletion mode, a channel exists naturally. So this fundamental difference in default state affects how circuits are designed and optimized, much like how the default position of mechanical switch influences the design of the machine it controls. Okay. Now let's take a look at the CMOS devices and circuits. So CMOS technology combines N-channel and P-channel MOSFETs together to create highly efficient digital circuits. Let's take a look at the circuit symbols. N-channel MOSFET has an, I have, yeah, N-channel MOSFET symbol has been drawn here, and PMOS, its symbol has been drawn here. So take a look at there is a small circle onto the gate electrode to indicate p-channel transistor. The beauty of CMOS is demonstrated in this CMOS inverter circuit, which is the simplest building block of digital logic circuits. When the input is very low, 0 volt, the p-channel, this p-channel MOSFET turns on while the N-channel MOSFET turns off, connecting the to output node, connecting to the VDD high. Okay, so when the input is instead of 0, input is 1 volt or VDD or high, the N-channel MOSFET is now on and P-channel is off. So this is like a seesaw. When one side goes up, the other side goes down. So what makes this arrangement brilliant is that in either stable states, one transistor is always off, creating a high resistance path that minimizes power consumption. This is similar to how a well-designed building uses airlock doors. One door must close before the other opens. You may use these airlock doors in a clean room. So, so preventing energy waste anyhow. So this complementary behavior is why modern processors such as CPU can pack billions of transistors onto a chip without melting from heat generation. Only during the brief switching transition do both transistors conduct simultaneously, making CMOS technology the foundation of energy efficient computing. Okay. All right. So now let's take a look at the pull down and pull up devices. So in CMOS logic gates, N channel and P channel MOSFETs serve distinct and complementary roles. N channel MOSFETs connect the output to N channel MOSFET here, connect the output node here to ground, acting as pull down, right? When they are turned on. P-channel MOSFET in this case connect the output node to the supply voltage VDD, serving as pull-up devices when they are activated. So think of this arrangement like a tug of war contest. Tug of war contest. The antenna transistors are team members who pull the rope downward toward the ground, while P-channel transistors are team members who pull upward toward the VDD power supply. The winning team determines whether the output is high or low. The beauty is that we never allow both teams to win simultaneously in static operation. that would create a direct path from power to ground, wasting energy, right? So for a given logic function, we construct complementary networks of these devices. The pull-up network consists exclusively of p-channel MOSFET, while the pull-down network uses only n-channel MOSFETs. So input signals control both networks in a complementary fashion, ensuring that when one network conducts, the other network is inactive. This is like a well-coordinated dance where partners never step on each other's toes. This complementary structure is the key to CMOS exceptional energy efficiency, making it possible for your smartphone to run all the day long on a single battery charge. You know what? In 80386 Intel CPU, the CMOS technology has been, for the first time, been adopted, and which can save tons of energy efficiency. All right. Okay, so now let's move on to the next slide. CMOS NAND gate. The CMOS NAND gate exemplifies the elegant logic implementation possible with the complementary transistors. Looking at the truth table on the right-hand side, we can see that the output F is 0 only when both inputs A and B are 1. Otherwise, the F is 1. Hence, the name not NAND or NAND. Okay. The circuit implementation for NAND function reveals the underlying symmetry of CMOS design. Can you imagine the symmetry of CMOS design in this NAND gate? Well, I guess so. The pull-down network here at the bottom consists of two n-channel MOSFETs connected in series. Think of this as requiring two switches to be closed simultaneously to complete the path to the ground. Both inputs A and B must be high to turn on both n-channel transistors and then pull the output low. Okay. Now take a look at the pull-up network at the top. Consists of two p-channel MOSFETs connected in parallel, right? So this is like having two independent ways to connect the power supply. If either path is available, right, this way or that way is available, the connection between power supply to the output node can be made. So when either input A or B is low, at least the one p-channel MOSFET turns on, pulling the output high. So this arrangement is analogous to home lighting controlled by multiple switches. In a staircase with the switches at the top and bottom, you need both switches in the correct position to turn off the light, NAND function, right? But either switch can turn it on. So the NAND gate's importance extends beyond its logical operation. It is actually a universal gate, meaning any logical function can be built using only NAND gates, making a fundamental building block of digital circuits, actually. All right, now it's time to take a look at the CMOS NOR gate this time. The CMOS NOR gate implements another fundamental logic function, actually. According to this truth table on the right-hand side, the output F is 1 only when both input A and B are 0. Otherwise, F is 0, giving us not or nor functionality. So in this circuit, on the left-hand side, the pull-up and pull-down networks are essentially inverted version of what we have seen in the NAND gate, right? Take a look at the here. Two MOSFETs are connected in series in the pull-down networks. However, herein, two NMOSs are connected in parallel right? Instead of in series. So in this circuit, the pull-up, again, pull-up, pull-down networks are essentially inverted version of what we have seen in the NAND gate. So the pull-up network now consists of two p-channel MOSFET, right? And they are connected in series. So this means both inputs, A and B, must be low to turn on both p-channel transistors and connect the output to the VDD in the end, producing a high output value. Now take a look at the pull-down network. The pull-down network features two N MOSFETs in parallel, right? In either input A or B is high, at least one channel, right? Here or there, at least one N-channel transistor conducts, creating a path to the ground, right? From here to there. So pulling the output node low. Okay? So this arrangement is like a security system where two keys are necessary to disable the alarm system. Both inputs must be zero to get a high output. However, either key can trigger it. Either input being one produces a low output. So the NOR gate, like the NAND gate, is also a universal gate, meaning any logical function can be constructed using only NOR gates. Together, NAND and NOR gates form the backbone of the digital computation, allowing complex decision making to be implemented through combinations of these simple elements, which is quite similar to how complex sentences are built from simple words and grammar rules. Okay. All right. Now let's take a look at the CMOS pass gate this time. So the CMOS pass gate represents a different type of circuit element, a controllable switch rather than a logical gate. So in its simplistic form, a pass gate allows a signal X to pass through to Y when the control signal A is active. So think of a pass gate as an electronic version of a bouncer at an exclusive club. When the bouncer control signal A recognized you, you are allowed to pass from the street into the club. When the bouncer doesn't recognize you, you are blocked, regardless of who you are. So in digital circuits, pass gates are crucial for building multiplexers, memory cells, and other selective routing structures. They allow signals to be channeled dynamically based on control inputs. For example, in a data bus, pass gates might determine which device gets to place its data on the shared lines at any given moment, similar to how traffic lights control which which lane of cars get to enter an intersection. So the unique value of pass gate is their bidirectional nature. Signals can flow from X to Y or from Y to X, unlike a standard logic gates where information flows in only one direction, as we have seen in CMOS, NAND, and NOR gates. So this bidirectionality makes them particularly useful in certain memory and analog applications where signals need to be routed rather than just processed logically. Okay. All right. So now let's have a small break time here. All right.